Hello everyone. Today we're going over the 1988 Putnam exam A1 problem. This problem is very accessible for the high school classroom, especially if Desmos is used. Okay, let's read the problem statement. Let R be the region consisting of the points x, y of the Cartesian plane satisfying both the absolute value of x minus the absolute value of y is less than or equal to 1 and the absolute value of y is less than or equal to 1. Sketch the region R and find its area. Alright, let's first look at the simple graph of f of x equals x squared. Geometrically, how can we make the parabola lay on its side? Well, we can spin it about the y-axis once, and then we can rotate it 90 degrees clockwise. Effectively, we've switched the x and y axes, creating a quote-unquote inverse, even though y equals x squared does not have an inverse because it's not one-to-one. These geometric rigid motions are equivalent to spinning or reflecting the parabola about the line y equals x. Now the new equation of the graph is x equals y squared. Now we want to use the analogy of the parabola to analyze this V-shaped graph, which is y equals the absolute value of x. Analogy is a problem-solving strategy. So what's the difference between the two graphs, the parabola and the absolute value of x is V-shaped? This one is not smooth. The parabola was smooth, but the difference is that the absolute value of x is not smooth. So what's the similarity between the absolute value of x and x squared? Well, every non-zero input becomes positive. When you take the absolute value of any non-zero input, it becomes a positive number. And similarly, for x squared, you put in a non-zero input, and it becomes positive. So we can use this to our advantage. Okay, so we want to do what we did before. We want to rotate the graph about the y-axis, and then we want to rotate it down, okay? And when we do this, we're going to get the equation x equals the absolute value of y. So this equation here, x equals the absolute value of y, constructs or gives this graph. So the idea is we want to use analogy to solve our problem. So we may not know what the graph of this looks like, but we do know what the graph of a circle is. It's x squared plus y squared equals 1. It sort of looks similar, but let's see what we can do. Even though the equation is different, it's similar enough to help us to solve the problem. We also want to look at the absolute value of x plus the absolute value of y equals to 1. It's actually this square here, right? Which is sort of like a circle. So, you can always plot points, right? You can always plot the point 0, 1, minus 1, 0, 0 minus 1, 1, 0. And then you get the idea of like, well, it's almost like a circle, right? X squared plus y squared equals 1. Absolute value of x plus absolute value of y equals 1. But this is just not smooth. It's a non-smooth circle. And then what happens when we put in an inequality sign? When we do that, well, we have the interior. Okay, because learning isn't linear, let's go on to an aside. So we want to talk about manifolds, okay, topological manifolds. The space X is a topological manifold of dimension n if for each point in the space X, so it has to be contained in the space X, there exists an open neighborhood also contained in the space X, which is homeomorphic to Rn. Okay, so the circle is actually just this outer boundary. It's not the interior, okay? So let's look at a point on the circle. So what does an open neighborhood of the circle look like? Well, it looks like this. And you see now, when we zoom in, what can we say? Well, this little space here, this neighborhood of the point, looks just like a straight line, right? So we can say it's homeomorphic to R1, or R, the real line. So this is a manifold of dimension 1. The circle is a manifold of dimension 1, or we call it a 1 manifold. Okay, so now let's check how the inequality sign affects the graph. X squared plus y squared greater than or equal to 1 gives this area here. So it's the exterior of the circle. So the interior is missing and it gives the exterior. Okay, so what happens when we switch the inequality sign to less than or equal to? We have x squared plus y squared is less than or equal to 1. Now we have the interior of the circle shaded in. Actually, what this inequality represents is the set of all points whose distance from the center to any other point is going to be less than 1. Because you can see if I just take the square root, this will be like the distance formula. Now this is a disk. It's a closed disk. It has boundary on it. So this is actually a manifold of dimension 2. You see, if we take any neighborhood of a point, we can find an open neighborhood. No matter how close we get to the boundary, we can always find an open neighborhood of that point, which is homeomorphic to R2. So again, around any point in the interior of the disclosed disk, if we take any point, we can find an open set containing it, which is homeomorphic to R2, no matter how close we get to the boundary. And you can see in the boundary, it's going to be the circle S1. So you can actually see that the dimensions of the the boundary are 1 less than the interior. Okay, so we want to go by the way of analogy. You may know the equation of a hyperbola, x squared minus y squared equals to 1. It's smooth, it's disconnected. Now we can finally draw the graph of absolute value of x minus absolute value of y equals 1. It's completely analogous. It's disconnected. It's just not smooth. Now, since we have the proper background knowledge from all the examples we went over, we can finally solve the Putnam problem. Okay, so you see here we have absolute value of x minus absolute value of y is less than or equal to 1. Okay, so that means that we're going to have all the interior, the area of the interior inside the curve, okay, less than or equal to. And then additionally, we have this condition that absolute value of y is less than or equal to 1. So in other words, y is bounded between -1 and 1. So we have this bound here, okay? If we didn't have this condition, absolute value of y is less than or equal to 1, then this would just be unbounded to infinity, but it would still be filled in here. Okay, so now we have this nice symmetric shape. In fact, it's composed of two trapezoids, two congruent trapezoids. And we want to find the area of them. So we just need to find the area of one and then multiply it by 2. So let's first look at a couple of things. So we have a point here. What is it? Well, it's going to be 1, 0. So when we're looking at the boundary, the curve, we're just looking at only equality, not the inequality. So if x equals 1, then y has to be 0. And similarly here, since it's absolute value, it's symmetric, right? So absolute value implies symmetry. If we play a -1, we'll also have y is 0. So we have this point here. And then this point here is 2, 1. How do you see that? Well, if we plug in the point y equals 1, we have to see that, well, 2 minus 1 will give us 1. All right, so now what's the general formula for the area of a trapezoid? It's 1/2 base 1 plus base 2 times the height. So we just need to identify these three things and then the calculation is easy. So let's first look at base 1. Where is that? So we're going to look at the shorter side here. This is base 1. So the two bases are parallel to each other, right, on the trapezoid. That's how you identify them. The two bases on the trapezoid are parallel to each other. So we're going to take base 1 as the shorter side, and then look at the red one, base 2. This is the second base. And then what's the height, h? So this is the height here of the trapezoid. All right, so now we need to find the value of b1, b2, and h. So how do we calculate this? Well, from 0 to 1 is going to be 1, and from 0 to -1 symmetrically will also be 1. So this has a length of 2. What about the long one? Well, the coordinate x coordinate here is 2, so this has a length of 2. And symmetrically, this also has a length of 2, so the whole thing is 4. What about the height h? Well, the height h is just going to be 1, right? From 0 to 1 is just 1. So we have our calculation here. And you notice the 1/2 is gone. The 1/2 is gone because I already multiplied this by 2 because these two trapezoids are congruent. So I'm just multiplying by 2. So we have the first base, which is a value of 2. We have the second base, which has a value of 4. And then we have the height here, which has a value of 1. 2 plus 4 is equal to 6. And this is the area bounded between these curves, which is the solution to this Putnam problem. Let's look at more ways to compute the area bounded by the curves. One such way is to view this as a rectangle. So if we do that, we can fill this space in with triangles. So let's do that. So now we have a rectangle. Now what are the dimensions of this rectangle? Well, like we mentioned before, this has length 2, this has length 2. This has length what? Well, this is 1, and this is 1. So this is going to have length 2. 1 plus 1 is 2. And then this is going to have length 4. Now, how do we compute the areas of the triangles? Well, the area of the triangle is just 1/2 base times height. So what's the base? Well, it's 2, and then the height is 1. So the area of this will just be 1, and the area of this will be 1. So we're going to get 4 times 2, which is the area of the whole rectangle, which is 8, minus 2, which is, again, 6. Now try to think of more ways to dissect or put together shapes in order to compute the area of this. Maybe one such way is to dissect this into triangles here and triangles here. And maybe another way is to take this trapezoid and glue it onto here to make a parallelogram, where it's just base times height. So some Putnam problems are easy. If you enjoyed this video, please hit the like and subscribe button now. Also, check out the links in the description for my book, Learning Isn't Linear. And remember, until next time, prioritize long-term learning over short-term test taking.